et qui fait partie des gens qui ont très tôt commencé à explorer des méthodes un peu novatrices pour les gros jeux de données. Voilà, et aujourd'hui, il nous fait le plaisir de venir nous parler de son travail récent. Stéphane, je te laisse commencer. Merci beaucoup. Hein.
Okay, merci, thank you. So I will, yes, today I will describe two aspects. So about the photometric redshifts and the challenge for the accuracy that we need on those type of measurements to, in particular, measure the cosmic web with the large imaging surveys that are coming, and so I will oops, sorry, I will come back. So basically, I'm working on this convolutional neural network with Marie Treyer and Haïd Ouamed at LAM, and with an expert on the topic, which is Jérôme Pasquet in Tétis, and we are collaborating with Emmanuel Bertin at IEP essentially, and Dominique Fouché, CPPM. And then on the other aspect, plenty of people from IEP, including Christophe, Clotilde, and Sandrine Collis. And so the talk will be split in three parts. So the first one is why to consider the cosmic web when to study the galaxy evolution. So I will be brief on this part. Then what type of accuracy we can expect for the PhotoZ in the future imaging surveys by using what we have currently, so from the SDSS and up to the HSC deep imaging surveys. So we will see how the things evolve with the different image quality. And then after that, I will very briefly show what we could expect to do then for exploring the cosmic web in since redshift slice based on the photometric redshifts with large imaging surveys to come. So briefly about the context, the cosmic web is a natural environment where galaxies form and evolve. It's where most of the baryons are located inside. So essentially in tenuous gas in thin filaments. So most of the gas is in the filamentary structure of the cosmic web, and 10%, about 10% in the circumgalactic environment of galaxies. And the rest is what we can see, which are directly the stars, so 10%. So the galaxies are very complex systems. There is a complex interplay between what is bringing in, so the infall materials that get inside the halos, the star formation activity inside the disk, and the feedback processes. So all these are contributing to make the galaxy evolving over time. So they get the gas from the IgM medium, and this gas can be in the very different phase, so cold or hot. And in particular, in the simulations, I've shown that the cold flows were a very an efficient way to trigger star formation and fuel galaxies at high redshifts to trigger very intense star formation at those epochs. And then the rest may be more dominant at lower redshifts with hot gas accretions. But at high redshift is really the cold mode that can be the dominant ingredients of the fueling of material. So the star formation rate in galaxies is a second ingredient. So the gas is transformed in stars, and typically the depletion time scale that we can expect in a disk at high and low redshift indeed is pretty short. So the star formation is quite efficient. So you need 2 to 1 giga-year to convert the gas in stars. So which means that this time depletion is always very short compared to the Hubble time. And clearly you need to fuel the disk of the galaxies to sustain the star formation activity. And the third process is the feedback. So all the events from energetic events like AGN, supernovae, and stellar winds will contribute to reinject the materials in the halos, which can then collapse again inside the disk and bring new gas. And so there is a kind of fountain scenario that could happen. So all these are very complex, and this is what will drive the evolution of the galaxies in this global context of the accretion of matter and gas. And so regarding the simulation, it's known since quite some time that indeed the cosmic web has an important feature. Basically, the filamentary flows can directly advect angular momentum into the halos and then the newly formed galaxies. And it was predicted indeed some time ago that indeed you expect that low mass young star-forming galaxies can have a spin which is indeed parallel to the filaments they belong to. And at high mass, you can expect some reversal trend with spin which is perpendicular to the filament, due essentially to the mergers along the filaments. And this type of prediction has been indeed observed in the SDSS some time ago. So, and which really reflects the interconnection between this large-scale structure and the galaxy evolutions internally at small scale inside the halos. And so in general, the halo accretion is really the process where the way the halo will grow with time. And indeed, this anisotropic cosmic web drives the accretion from the past and the current accretion inside the halo. So same halo in the simulation that belongs to very different environment, for example, in very massive filaments, or in the connection of plenty of small filaments, can have experience completely different accretion. So at a given mass, it can continue to accrete or be completely stalled in terms of accretion, and then its future evolution will be different. So, so you expect the environment to be a considerable influence in the evolution of those halos. So with this short background in terms of influence of cosmic web on halo size, we can also try to see if there is other ingredients that we can detect on the influence of the cosmic web on the galaxy properties, like some quantities that are more integrated, like stellar mass or star morphology and specific star formation rate. And this was accessible last 10 years with different large-scale spectroscopic surveys that allows us to derive those physical quantities through the cosmic web environment. Basically, by characterizing the position of a galaxy with respect to the large-scale feature of the cosmic web, so the walls, the filaments, and the nodes of the cosmic web. So, and then study the distribution of properties according to this new metric represented by the cosmic web. So this is an illustration of the Vipers surveys at redshift about 0.7, where you can see the galaxies and the filamentary structures run by the dispersed code developed at IEP by Thierry Sousby. So doing that, there were some evidence of the influence of cosmic web, this shown by the SDSS, for example, on the left, where you can see that galaxy near filaments tend to be slightly more massive in red than the galaxy away from filament at a given density. So beyond the density, which is a well-known dominant factor in galaxy evolution, you still see specific influence of cosmic web, whereas the galaxies tend to be slightly more massive. And this is significant in terms of uncertainties compared to the galaxies that are away from the filaments. And the same thing in Vipers, for example, on the right, where we see that the star-forming galaxies tend to be slightly at a larger distance than the passive galaxy in the same stellar mass range. And this effect is preserved even after reshuffling and respecting the density, morphology, and mass properties. So this is some type of signature. There is also a nice way also to see that is that when you study the stellar activities or SSFR, the specific SFR, you can see a gradual evolution according to the distance to filaments. So the galaxy, when you renormalize everything according to the stellar mass, you can see that galaxies have a quite constant star formation behavior. So a steady state at not too close to the filaments, but in the neighborhood of the filaments. So where they basically have the star formation activity, and then they continuously fuel the gas reservoir to continue to consume the gas and form stars. And when they get very close to filaments, you can see that there is a sharp increase of the SSFR, so basically a reduction of the star formation efficiency. So that shows that some mechanisms prevent them to continue to have access to their gas supply. So And and so there are many other evidence that has been found in different experiments. So basically showing the influence of the cosmic web as large beyond the classical interpretation of the density or halo mass prescription. That is the main way to describe galaxy evolution in general. So it opened kind of an interesting door, but we are limited to the few spectroscopic surveys that we have. And indeed, recently, Clotilde L'Aigle has shown that we can have this type of approach also with photometric redshifts. So she did it in a well-known survey, which is a Cosmos field, where you have 30 bands, so pretty accurate photosy, better than 1% accuracy. So sigma-z, typically what we will talk very often during this talk is the sigma, so the accuracy of the photometric redshift, which is about 0.01. And then by making slice of delta Z of a few hundred of megaparsec, she can show that she can recover the filamentary structure in 3D, in 2D, and in the photometric redshift space. So, which is a very good indication that this type of work can be investigated properly. And she also recovers some segregation effect that she was able to detect in 3D. And she do the same thing with the simulation and find exactly the same behavior. So moving from 3D to 2D and to photosy in 2D, she can still detect some segregation effect. So it's very encouraging. So showing that we can, but the main point is this is Cosmos field, so with 30 bands. So can we imagine to do that with future generations photometric surveys, which are a very limited number of bands, but typically 5 to 6. And so, which roughly means if you want to work at this type of redshift slice of a few hundred megaparsecs, so between 100 and 200 megaparsec, let's say, we really need to get accuracy about 0.15, 0.015, or maximum 0.02 to be able to do this type of exercise. So, and to control well the bias in your photosy over the redshift. So that brings me to the photometric redshift technique. And so there are basically two large families of photometric redshifts. The SED fitting, which is a standard approach. So your prior is that we know the galaxies, so we are able to build SEDs for the subjects. And then based on that, we can redshift those SEDs and get the best redshifts that match the photometry that we are observing for the subjects. Another approach is we don't trust anything and just a spectroscopic redshift. So you use spectroscopic sample, so with non-redshift, and basically you ask machine learning approach to use your input photometry, which can be flux, colors, or whatever, this type of quantities, and ask to map this to the redshifts. So there are many methods that has been developed in machine learning over the last 10 years, and I will not go into detail, but basically in these two approaches, the main factor is that they are using extracted information, which are either the flux or the colors, and to get that is already a process, because it's not trivial to extract robust colors and flux, even with a well-known extractor tool. Is still challenging to get, and also we know that we are not using all the information, because you just limited your information to the flux you measure inside the given aperture or so. And so all the rest, which is in the images, is lost. Basically the surface brightness, the size, the inclination, color gradients, all this information is lost. So a nice alternative to that is indeed to go with convolutional neural network, which use directly the images as input instead of extracted feature. So that was recently shown to work indeed with JPEG images by Oil, where he shows that indeed he can, by combining some JPEG images colors, he can get a good photometric redshift estimate from that on the SDSS. And predict some PDF for that. So this was obviously doable because of the large spectroscopic sample he was using, and also because of the apparition of the GPU at that time, so which allowed to make a lot of intensive computations. And so in this idea, so we develop our own CNN to do this exercise. So just I will briefly do a brief introduction to the deep neural network and the CNN later. And I put the link, I use the slides, modify the slide, but the slides are based on the Fidel talk that is from the people from Grenoble. And they are very nicely illustrated. So I use those in the next few slides. And so basically you have on the right, on the left, you have your inputs, which are depend, in our case, can be magnitudes, colors. And those inputs are connected to networks, hidden layers of network. And so what will do the network is to connect all the input together in one network, and we'll combine the information. You see what does one single network in the upset on the top right. It will just combine the different, put a weight on all the input together and apply an activation function that will introduce a small nonlinearity. So the small nonlinearity can just be 0 if the combination of all the weight is below 0, and just the x value if it is above. So this small nonlinearity introduced by one specific neuron is then propagated to another next layer where they are all connected together to produce another nonlinearity in the system, and so on. So basically, the deeper you go, the higher the nonlinearity you introduce in your system. And so, and at the end, you recombine all this network in all this layer in one output layer, which can be, in our case, either a regression, so you just ask for one value, a redshift, or it can be a classification. So basically, you can ask many output, which are all the redshift bins that you decide initially to get. So that will be a classification inside the redshift bin. And so in these models, we can see that there are many weights that will be applied to each layer. And so difficulties is to train the network to be able to find the right weight in your system when you have, where you can have millions of weights. And indeed, here it shows pretty well how you can train the deep neural network in this procedure. So basically, the top at the center is what I just showed. So this is the deep network. So you enter a batch of input value, you process through the network, you get some predicted output, and then you will confront this output to the expectation of your trained samples, so what value you expect for y. And this is what we call the loss function. And basically, the loss function will depend on what you want to do, a regression or a classification. But at the end, you have a loss function that you can indeed optimize for every weight thanks to the back propagation, which allows to derive indeed this the cost of the loss function and to improve the loss function according to every parameters in your network. So this is the big progress in the deep neural network, was this back propagation process, which follow a gradient descent, indeed, and which allow you to update for every layer. So they know now with this process to propagate through several hidden layers without any problem of vanishing gradients. So you can propagate through all the layers and optimize your weight up to the input weight. So in this way, what you do is not to run all the input at once, but you do mini batch. So you run set of images or input value, 60, 100, and then you repeat and you converge slowly on all your weights are converging slowly until you have done an epoch, and then you can reprocess it through several epochs to improve the network. So this is the way the system works to find the proper weight. And so to avoid problem of overfitting, one simple way, which is indeed what we are using as well, is to split your input data set in 80s for the training set, so which is used to train the weight. And in parallel, you do the inference with the 20% of the remaining. So you go through the same network, which is already trained from the top pass, and you see the performance you get. And the training part will always get better and better, while at some point the test sample, which is not seen in the training, will start to get less good. And this is typically where you can define the epoch where the network starts to overtrain on the overfit on the sample is training. So that's indeed the way we are also using the network to avoid the overfit. So this is for the deep neural network part, but so you can use either quantities like colors and magnitude, in our case for the photometric redshift, or you can put images. Obviously, if you put images, that means a lot of information if you use every pixel, so you cannot directly connect images to this deep neural network. So you need to go through some process first. And this process is what is called the convolutional neural network, so developed by Lequin in '98. And the idea is you start with your images and you apply several convolutions through those images with different kernel size, and then you will use the output of this convolution to process again with new series of convolution. In between the different convolution steps, you can also decrease the size to do some pooling to compress the information in a smaller size. And then, so to reduce the final size, you will connect to the deep neural network. And so in this process, you are extracting over time more and more abstract features contained in your images initially. And so that's a way we are doing as well. So you do the convolution in several steps with some pooling, and at the end you connect what we call the feature map. So all the final information you have collected about your images, which is compressed, which will be connected to the fully connected layers to get the classification or your redshift estimate. So in our specific case, the initial code that we have developed by Joanna Pasquet was exactly that. So we have 5 convolution blocks, and which use also some pooling. So we reduce the size over time. So, and at the end, after the inputs, after all this convolution, we get about 30, 50 feature maps that are directly connected to the fully connected neural network to get the classification. We had one extra parameter that I will explain later. So with that, we use the network as a classifier, and not we don't do a regression. So which means that at the end, we put a softmax so we can distribute the weight through the different class of redshift, and which allows us to get a PDF for every single galaxy. So this network, the initial network, has this 27 million parameters. One more step beyond the cross-validation that I already explained to split the sample into in 80% and 20%, and we repeat that 5 times. So the 20% contain every time a new part of the sample. We also, because you start with some initialization for the weights of the network, and those initialization are random weights. So we do 6 ensembles for every cross-validation. We do 6 ensembles, so which means that we start with 6 random realization on the same training set. Okay, so basically you can average the value of the 6 ensemble to get the final value for the training set. And ultimately, all the cross-validation are also combined, where we combine the value of the quantities itself, the performance. So the sigma, the delta z, the bias, and the catastrophic fraction. So this is the scheme of what we are doing in this CNN. So now we start. If you have any, just let me know if you have any questions, because I can be a bit slow. I will try to speed up, maybe because it will be too long. So I will start with the SDSS, which was our initial work, and so which is the main galaxy sample of the SDSS, about 500,000 galaxies, and relatively low redshift, obviously, so below 0.2, 0.3. And this is the full map. So here are some of the results. So just to illustrate the PDF that we get with the SDSS analysis. So you get the image and the PDF. So, so you can see that those PDF are quite smooth, indeed. And so the final results of the comparison between the spectroscopic and the photometric redshift estimate in our case. So with the CNN, it's on the left. And on the right, we compare with what the value provided by the SDSS final release of the PhotoZ, which is the one from Beck 2016, based on the nearest neighbors technique, so KNN. Okay, so machine learning approach as well, but just using the photometry as input. And so you can see that we have again on the mean bias, which is the mean delta Z, which is pretty flat in our case, and about 30% in the sigma, so in the accuracy, in the sigma Z, which is pretty good, and also in the fraction of catastrophic failure, which is much lower in our case. And so as an information, we indeed, the latest versions that we have of the code give even better results because we get to 10 to the minus 3 of accuracy now, and we reduce again the catastrophic rate. So to quantify the PDF robustness, basically, we use what is standard indeed to quantify this quality is the PIT, the probability integral transform. So basically, you know what the redshifts are, the spectroscopic redshifts, and you check the fraction of the PDF which is below this this value. And statistically, over the full sample, if your PDF are statistically robust, you expect that all value of the PIT are equally distributed. So you expect the histogram of all your PIT in your sample to be flat. So, and indeed, if you get a PIT which is, as I show in green, which doesn't have value in the extreme, that typically means that the PDF are slightly too large. So you never get the PhotoZ, never the SpecZ never probe the full PDF. So your wings are way too large. And on the other sense, if you on the opposite, if your PDF has too narrow, you will have many value of the PIT that are indeed at 0 or 1. So that means that your PDF are intrinsically too narrow. So in our case, which is the blue shaded blue histogram, we are a reasonably flat PDF, which is a PIT distribution, which is a good sign that PDF are properly balanced. And so since the sample is very large, so we can explore how it behaves with different properties. So basically what you see, so in green is always the result from the Beck to 2016. And in red is our result from our CNN. And so what you can see is as a function of the signal to noise of the images, obviously you have a big gain. So it decreases quite a lot with the high signal to noise images. And one important ingredient was the galactic extinction, so our Milky Way extinction. And indeed, so in green is the Beck result. Beck used galactic corrected magnitudes. But you can see that he still have an effect in the bias as a function of the EBV from the Milky Way. And in our case, we have a very strong bias because initially we were in orange. And so we have a strong bias with extinction, galactic extinction. And that was the reason why we include the EBV value as input before the fully connected network. And this improved the final results by putting the red line, which is now perfectly flat and independent of the running excess. Another very nice quantity is the inclination of the galaxies. So when you get very inclined galaxies, so this is stressed by the B over A on the right top panel, and you can really see that the bias, in our case, we have no bias with the galaxy inclination, which is extremely good because that really means that it can handle it properly. And this is something that we can't, unfortunately, do with acid fitting as well. And we have to, and you can see that the result from the KNN shows still some bias with the inclination. So we cannot properly account for this inclination effects, which is clearly well done in the CNN approach. One other important ingredient is the size of the training set. So we cut the size of the training set in 2, in 5, and in 50. And at the end, the results are shown in the red square. And you can see that you basically up to 20% of the sample size, if you only use 20% of the sample size, the sigma is almost the same. So which is pretty good. So basically we can decrease quite a lot the sample without gaining a lot. So we clearly converge quickly on a value which is reasonable for the CNN. So you don't need too large sample. And finally, even 2% of the total sample size is used for the training. We get about the same accuracy than Beck, just by using 2% of the full sample for the training. So which clearly means that we don't necessarily always need a huge training set to get reasonable results. And so here is the homogeneity of the bias of the photosy. Is a spectroscopic survey that go 2 magnitudes deeper than SDSS. It's the 3 fields that we have access to on the SDSS with the SDSS images, sorry. And so here we will train on this spectroscopic data set, which is about 150,000 spectra, that goes up to redshift 0.6. So we go a bit further in redshift and fainter in magnitude with obviously much fainter images, with much lower signal to noise images because we are still using the same SDSS. So here is the results. So the original SDSS is in orange. And when we train on gamma at the same depth as the SDSS, we get slightly worse results. So it's not as good because the training is much smaller at this bright magnitude. And as we go fainter and fainter, so you have 2 other bin of redshift, of magnitude. So you can see that we get a slightly degraded accuracy in terms of photosy, but stay relatively flat in terms of redshift. But clearly, when you decrease the signal to noise of your images, you see the impact on the sigma of your population. So basically, you get about 0.025 for the faintest magnitude bins. So, which is quite good compared to the result from Beck. There is still an improvement, which is not negligible. So that's why we decide to indeed to release all the SDSS. So we are using the 20 million sources brighter than R20. And we will release the full SDSS photometric redshift with this CNN and their PDF probably this spring when we need quite a lot of space and computing power for that. Another interesting point about the gamma survey, we have a common region with the CFHTLS, which is so the megacam camera at CFHT. And so one of the gamma field is located in the CFHTLS wide. So in that case, we train the same spectroscopic sample in the common region. We train it with the CFHTLS images. So you can see the gain between SDSS images and CFHTLS images. So you can see the details of the galaxies that show up clearly. And so when you do that, so you have much smaller sample because CFHTLS is not everywhere in gamma. But still, you have a jump in accuracy in terms of sigma. So we can get about 0.01 or close to 0.01, a factor 2 improvement compared to when we use SDSS images. So a big gain by changing the data, the image as input. One, just to check, how long can I be?
You can continue.
Just let me know. So I probably would not go to the end, but just let me know when you really want me to stop. So, this the nice steps that we have shown in the SDSS. So it's one interesting step. But then there is another approach which will be feasible also in the near future, is that we will have spectroscopic surveys that will overlap photometric surveys, obviously. And then you can try to, if those spectroscopic samples are dense enough to probe the cosmic web on large scale, then you can project your photosy inside this cosmic web drawn by the spectroscopic sample. So this is an illustration on the top and on the right from Aragon-Calvo, where you see the density field in the SDSS, so the density of galaxy measured with spectroscopy. And then you will use your objects, so this is a line of sight in red. You will use your objects with the PDF, which is a weird Gaussian that I show. And this Gaussian can be projected through the different peak of density that it will cross along the line of sight. And so by doing that, by combining the probability of this estimate, you can end up with a much narrower photosy peak at the end. So we have done this exercise with Marco Shentov, who is in Paris now. And so we can combine, we have used the cosmic web reconstruct by combining the main galaxy sample and the BOSS sample. And we have used a sample of galaxies from SDSS that was not used in the reconstruction of the cosmic web. And what we get by projecting our PDF through the cosmic web reconstruct with the spectroscopy, what we get is shown on the left, again, is the Z-web, what we call Z-web as a function of the spectroscopy. And on the right is the initial value of our CNN. And you can see that we jump again in terms of accuracy by a factor of 3 in terms of sigma. So we can really anchor your PDF through the structure where the galaxy is most likely to live, and which is pretty nice. And again, if you cut in terms of accuracy of PDF, so using the much narrower PDFs, you can again improve the sigma. So you see on the bottom part the delta Z over 1 plus Z, so the sigma, no, delta Z over 1 plus Z, for the original CNN in green, and for the ones that we built after passing through the cosmic web. So we can see a big improvement, and basically 50% of the galaxies in the Z-web have accuracy better than 10 megaparsecs in this way. So, and globally, all the population show an improvement. So 75% of the CNN have improved compared to the not using at all the cosmic web information. And if you want to know exactly which population are impacted, indeed, you need to start with a PDF, which is quite narrow. And only objects with PDF narrower than about 0.03 can have an improvement in the final redshift. So not picking a random structure along the line of sight. So that's, and obviously, if you study groups of galaxies, you get even better improvement for the photosy, because you already have some dense clump from the spectroscopy. And an illustration of what you end up, so the redshift, the distribution as a function of the CNN, and then as a function of the Z-web, where you clearly see that you have anchored the galaxy through the cosmic web, and you can start to reveal the cosmic web. So this type of technique is interesting because it will really depend on how you are able to reconstruct the cosmic web. So here, in our case, it's pretty high resolution cosmic web because it's about 6 megaparsecs resolution. And so, but if you go with the next generation of survey at higher redshift, we'll probably get something to typical intergalactic distance, about 10 to 12 megaparsec, and better with IgM tomography, by the way, at even higher redshift. And so, if we have enough accuracy in our PDF for the photosy, we could imagine to reproject the galaxy through this cosmic web, reconstruct from a spectroscopic survey like PFS or Euclid, or WFIRST and so on. But basically, it's really dependent on the PDF width that we will have for our main population of photometric redshift galaxies. So now we will move to, so that's it for the low redshift part. So I will go a bit faster, sorry, I didn't realize I was that long. So I will move to deep imaging surveys and much higher redshifts, where you start to have problems in the homogeneity of the training set. And so to do that, I combine several spectroscopic surveys together. And in what we would call the training set is all the very famous spectroscopic survey available at that time, and also some specific low resolution spectroscopic survey like based on the GRISM or a PRISM which are basically Primus and 3D HST. Some others are not used, but I will show some comparisons. And I will show some comparison with Cosmos 2020, the latest version of the Cosmos field photometric redshifts. So let's start with CFHTLS. So here you have the redshift distribution of the spectroscopic sample used for the CFHTLS at bright and faint magnitude. And so you get an idea about how good is representativity of the spectroscopic sample. So the red are the regions where you get dense sampling, and in blue and intermediate color, so sampling is lower. And this is redshift versus magnitude. So you immediately see that up to 23, 23.5, you do have a pretty good sampling in terms of spectroscopy. And up to 25 is acceptable, but start to be pretty low. So you have really an unbalanced population between the high redshift and low redshift, and also between the bright and faint. So in our training, we train together the CFHTLS wide and deep. Okay, we don't make distinction, so we know which come from which, but the CNN learns to work with both data sets because it's exactly the same images, except that the signal to noise is a bit higher for the deep. And so here are the results. So always present in two forms. So the sigma is a function of, so redshift versus redshifts. So you have the CNN, I compare to the photo-Z from the SED fitting provided by the CFHTLS. So you really see that from the right to the left, yes, there is a big gain about a factor 2 in accuracy with the CNN. And you can decompose that on the plot below, where you see the sigma as a function of redshift. And so you do get something better at almost 0.015 up to 0.7 in redshift. And then it starts to degrade when you move to higher redshift, okay? And there is almost no bias. So the delta Z over 1 plus Z, the mean delta Z over 1 plus Z, up to redshift 1, show almost no bias. So in blue is the SED fitting behavior, so which is clearly above. And in purple is when we select the CNN, only the one which have a PDF, which are the narrowest. So we reject 20% of the widest PDF. So you see that playing with that, you can still improve slightly the results. So going in the deep part of the CFHTLS, the results are pretty impressive. So we don't use the near infrared at no time because we are just used with UGRIZ for the CNN. While in that case, for the deep, there is a near infrared information that is included in the SED fitting. Okay. And so what you can see again is there is almost a factor 2, more than a factor 2 improvement in terms of sigma. And when you look at as a function of magnitude and redshift, so there is a bright part on the left, faint part on the right, you can clearly see that we get about 1% accuracy up to redshift 1.5 in the bright part, and with no bias. While in the fainter part of the population, so 23 to 25, you see less good, but still about 0.02 accuracy in sigma. Up to 1.5, which is pretty good considering that we don't have near infrared at all. Okay, and then it degrades at higher redshift. The bias is less well controlled in that case. So, so I will skip that. So just one word to say that we can also compare with the 66 photometric bands surveys from PAO on Cosmos in the Cosmos area, and so in orange is what they expect, what they are measuring as a function of magnitude. And so the sigma is a function of magnitude in orange from PAO with 66 bang. And in red is what we get in the deep for the accuracy we get as a function of magnitude. So we are comparable to Cosmos 2015. And but still, we still have so 5 bands are not enough to get highly reliable photo-Z as PAO, obviously, with 66 band. So I will skip that. So the behavior is as expected, so pretty good. And for then so on the HSC, so now we are moving in even deeper images, so about 26.5, 27. Those images are typically similar to the LSST. So that's why they are really interesting. So a small area, but 25 square degree, where we do have the U band up to the Y band. So UGRIZY. So, and we will compare now to what we have done with Vincent Piquet, with his PhD here, who is using LEFAR and combining the HSC cloud, so UGRIZ, plus Galex and near-infrared when available. So we will compare his photosy to our photosy with the CNN. So it's both our photosy, but to distinguish the two. And so you see that you get reasonably good photosy with SED fitting from LEFAR. And the data, we hope to release all the HSC clouds, so HSC plus U-band catalogs this summer, okay, with the photosy as well, and probably the CNN if we are ready to release them. So here is just to illustrate the spectroscopic distribution of the sample. So clearly we have a good sampling at bright magnitudes, brighter than 23.5, and below 23.5, the sampling is met in terms of spectroscopy. So the training sets will be quite critical, and below 25 is really critical. So we have almost nothing to train. So really poor. So we will see how it impacts our results. And so, taking at face value, I compare LEFAR photosy on the right and the CNN for the full population that we get, and you get very impressive results. So again, with these extremely deep images, we get a level of 0.012%. But obviously this number is misleading because it's really depending on magnitude and as we will see. So by splitting into regime of magnitudes, on the bright and faint part, so again, it's exactly the same plot as for CFHTLS. So you can see the CNN behavior. So we are really at 1% level accuracy in the bright part, up to 1.7 in redshift. So it's extremely consistent and extremely good, okay, which is about factor 2 better than what we get with LEFAR and SED fitting. So it's really impressive. And at the faint magnitude, in the faint magnitude regime, which is basically 23.5 to 25, we get still pretty good photosy. It's about 0.02, up to same redshift 1.5, 1.7. And again, the high redshift tail is really problematic. So we do not get very good results, and SED fitting can do even better. So now I will skip. Okay, now we will compare. So that was a comparison with spectroscopy. We can have a completely external comparison with Cosmos 2020, which is the last version of the 30-band photometric redshift catalogs from Henry and his team. And so it combines the U-band from clouds through the deep HSC images, intermediate bands, ultravista, IRAC. So it's a very large, impressive amount of deep data. And they have generated 2 catalogs for the source extractions, extractor and tractor, and 2 photometric redshifts. So what I will use to compare with is indeed just combining the 4 photosy together. So the 4 photosy from Cosmos 2020. So it's a mean of all the photosy. And so here are the comparison. So basically, I do compare the SED fitting is referring to our work on HSC, okay? The CNN is our code, and what we assume to be the truth is Cosmos 2020. So it's a comparison with Cosmos 2020 on the 2 versions. And so again, you can see that the sigma at bright magnitudes is excellent, and it's about 200,000 galaxies to compare. That we are comparing, okay? So up to 24, we really get a very excellent agreement with Cosmos, okay, about 0.015. And then when you go at faint magnitude, interesting part is SED fitting get better. Our SED fitting from HSC get better, but indeed, it's a similar code than Cosmos, so it's not very surprising. And our training set is extremely poor in that case. So again, to illustrate the 2 regimes, so the brighter than 23.5, you can see again a perfectly nice behavior in terms of redshift with the accuracy of photosy about 1%. And at faint magnitude, we are up to redshift 1.5. Again, we are better than 0.02, up to magnitude 25. So we still get pretty good photosy with some bias, as you can see on the high redshift tail, but it's still pretty robust and very small fraction of catastrophic failure, where the training sets start to be critical. Okay, I will skip that. And then the extremely faint regime is interesting because here you have almost no training in that particular regime, so which is shown here. And you can see that then you start to have some waving behavior between the two photosy, strong catastrophic fraction, and sigma, which is not that good. And so clearly we start to miss training set, and the acid fitting is doing much better. So the blue line is much better than what we can do in our case because of the training set. And basically, you get this plume of this CNN at low redshift for Cosmos, so which is on the vertical plume at low redshift that you can see, is basically because we have nothing to train. So the CNN doesn't know which redshift to attribute, so they get distributed all over. So there is one easy way to fix this type of thing, if we believe Cosmos is true, is to train, to add a population of Cosmos 2020 objects, a small fraction, about less than 10%, that populate the faint end and over all the redshift domain. So you can see the redshift distribution of the added objects in our training set. So when you do that, obviously it's improved. So this is the results before including some photosy from Cosmos and after including those photosy. So you can greatly improve the photosy in this faint regime, about 2% accuracy, and all over the redshift range, with still some waving behavior around redshift 2, where probably the near infrared will be needed at some point. But you can get a reasonably good agreement with photosy from Cosmos if you include a fraction in our training set in that regime, because we don't have anything else. Okay, so and again, if you slightly filter the PDF by rejecting 10% of the widest PDF, this is what you get at the end. So using a mixed training set for the CNN, so with good spectroscopic sample when available, and when you are moving in a regime where we don't have choice, using some fraction of photosy which are used as reference, then you can basically work pretty well on the full Cosmos sample, even up to very faint magnitude like 26. So there will be many different ways to improve that, but that's basically it. So at the end, I think we are converging to what the best we can do with the current training set with this approach. And so the main ingredient that we will need to probably work again is to incorporate the near-infrared images that has not been used. So that will certainly improve slightly the high redshift part. But that not only, the main point now is really to start to behave differently. So far we have just used the supervised approach for the CNN, and we want to extend a bit more in the unsupervised direction. So basically to be able to use some unlabeled data and to incorporate that in our learning process. So, and this also to try to mix the different domains, so to do some transfer knowledge between different domains where you train on one HSC and CFHTLS simultaneously. So to benefit from the training set of the two samples. So this is what we are exploring now. So this unsupervised or domain transfer, and this has been shown to work. Indeed, on the SDSS, some people have done this type of approach with what they call contrastive self-supervised learning. Basically, they pre-train the representation of the images using data augmentation of data without label, so without label in terms of redshift. So just use the similarity of those images, unlabeled redshifts, and when they have built their latent space or the representation of images with a large fraction of unlabeled data, they can use a fraction of it which have label to finalize the training and to classify the objects in terms of redshift. And doing so, they show that basically they need 4 times less label to get similar performance than a fully supervised approach. So you have gained to include unsupervised data, to include unlabeled data in your training. So basically by a factor 4 in terms of quantity of training set. So you can reduce the training set just by including unlabeled data. So which is interesting. And at the end, they show that having the full 80% of the labeled data plus all the unlabeled data used, they can get better results than us and the SDSS. Indeed, not really, because we get the same performance now, but the idea is here. And so we are doing that now with Jérôme Pasquier, who is developing this type of similar ideas. Basically, the idea is to use two surveys that have a common area, so where we know that we will have common objects. And so it's to combine the two domains together to do the training of the spectroscopic classification. And then when you get data with unlabeled value, but that belong to the two survey, so to the two domain, you try to minimize the distance in the latent space between the two representation of the data in the two domain. So by doing that, even if you don't have the redshift, you can use, you can force the sample to optimize the latent space that will be used then for the classification of redshift. So you try to make the two domains to converge to one single join latent space that will optimize, that will have the benefit of the two samples. And that's the idea that Jérôme is developing right now. So we don't know yet what we will get. But the main point is you just need to have labels in the two domains that are common. And the objects that are common, they may be without any redshift. So you just use the similarity in terms of images. Okay, so you can benefit having the redshift as well, but it's not necessary. So you can clearly increase the sample by using objects in common between the two. On the other side, REDA is developing a more complex approach because the idea is still to have some domain transfer, but in this time without any common sources. So two domains with no common objects in between the two domains. So this is a bit more complex because then you need to go through some variational autoencoder. So you construct your latent space with your two domains, and you try to get you try first to reconstruct the images specific to every domain, to the two domains. Okay, so you have an unsupervised part where you play only with the images, so without the label. Okay, and so you try to optimize the common latent space between the two, and just trying to play with the domain one, you try to reconstruct the image from the domain one. With the domain two, you try to reconstruct the image in the domain two. And then with some label data, you optimize this latent space to get the proper classification in terms of redshift. So you use the fraction of label data in both domains. Okay, so you improve the latent space that was used before the fully connected. And then when you get trained with some spectroscopic sample, you can start to play with some adversarial approach where you will try to fool a network that one object that is generated come from the other domain, and you will try to have a discriminator that decide which domain the galaxies you are showing belongs to. And indeed, when you are able to show that indeed domain one, the discriminator is not able to distinguish for the one in domain two, which means that you are starting to build the right latent space where you cannot anymore discriminate between the two domains. So you have your perfect reconstruction of the latent space, and then you can use your supervised approach to train the fully connected and get the redshift at the end. But here is more complex because you have no overlapping sources between the two domains. So that's another approach that REDA is developing right now. So it's a bit more complicated and not very stable so far. But we have good hope, and it has 3 years to develop that. And but basically, that's the idea is really to push in the direction of unsupervised and unlabeled data to really exploit as much as possible the images. I think I will stop here because I've been quite long, Philippe.
Okay, thank you very much.
Okay,
Stephane.
so just to I skip. So just to conclude, so I think we are, yeah, it's we have good hope with this approach of CNN, we don't have the same floor that we have with ACD fitting. So we clearly see that with ACD fitting, we are hard time to get better photosy. Here we see the benefit really of using the images. So and we can get to an accuracy which is better than a % level, depending on the signal to noise, obviously, but you can really get better at the level of 1% and better if you restrict yourself to some reasonable signal to noise and where the training set is good. So there is really good hope for the large surveys that we will get impressive results with photosy, even with a limited number of arms.
Thank you again.
So sorry, I was a bit long.
No, don't worry. So questions maybe for Stephane? So Benoit?
Yes, I have. Maybe I may have missed something at some point. First, can you tell me if I'm right that the way you derive a PDF is just by considering the weight given to each class of redshift bin?
Yeah. At the end, we have a softmax, so
okay. And then my question is that about the interpretation of this PDF. This is not quite exactly what physicists would call a PDF, right? I let you say what you want about that.
So I'm not a statistician for sure, so I will not. So my only we know that it may not be a perfect PDF, so because there is probably some posterior information that we should use. But the only thing at some point that matter to me, if and you will disagree also, to use the PIT as a pertinent information to test the quality of your PDF. But at the end, what we have found is by using some statistical estimate of what our PDF are providing us, like the probability integral transform, or there is also some other estimate statistical estimate that you can use. We find that our value are behaving as we expect as a PDF, are behaving in a consistent way as a PDF. So I don't know if it's not exactly what the statistician will call a PDF, but clearly,
actually, from a statistician,
it behave in the right way.
Yeah, but I'm not either a statistician, but it's just that even in the field of machine learning, they have devised some tools to separate in those uncertainties of the results what comes from your data specifically and what comes from the imperfect learning process from your network. Those are not trivial to use, those tools, but things like, well, using Bayesian neural network does not do the trick in itself, but then when you use them, you can try to separate the two sources of uncertainty. And I wondered if you had considered going in that direction, or not for now, and you have more important things to do for now.
At least we were confident in us with this PIT estimate about the quality of the PDF. I think for us, it's good enough right now, because we have other things to consider to make things working out. But I'm sure we will come back to that. to this to try to get the better estimate of really the uncertainties. But what was really encouraging is from the beginning with this PDF based on the class, the weight that we get at the different class, we all from the beginning we get this the pit indicator, which were pretty good, and so that was our main concern, is to have some reliability in the PDF, and we thought it was good enough.
Okay, thank you.
But we had criticism about that. But in the Photo-Z domain, so far, I haven't seen any better approach. So we are all using this pit indicator as a probe of our quality of PDF. And we use the classification to get the PDF indeed, instead of just doing a regression. That could have been done indeed. Indeed, we are mixing the two. We have regression and classification, but yes, we immediately go through classification to get those type of what we call a PDF.
Okay.
We should probably not, but
Rodrigo?
Yes, it was a really lovely talk. Thank you ever so much. I've learned lots of stuff, and it's really fascinating. So one of the things that when you said that you do you make a classification rather than a regression, why is that?
That was the initial, because we can, you are not limited in terms of number of class. And so it was interesting to be able for every object to attribute the probability to be in a different class. And the class is just a bin of redshifts.
But that kind of makes it naturally a regression problem, though, right?
But it's different. So then you just, it's just at the end that the loss function is not the same. So you will have different loss function. One is RMSE, the other is a cross entropy, and but basically it's exactly the same problems that it doesn't change the complexity of your network. But
so what happens when you do? You must have tried that, right?
But you always get the PDF of the object. So that was a interesting way to do to treat that as a classification problem.
And that was the only reason? Because
at the beginning, yeah, because initially we thought it will be a regression problem. Because you just want one value. At the end, you want the true redshift. And but then since we thought that we give a try to the classification, and we find that what we get at the end as PDF, what we call a PDF, has a very nice behavior according to the pit statistic.
Right. Okay.
And then we stay with that because compared to others, we get very nice behavior of pit.
Yeah. I mean, you could have done the same thing. I mean, I gave a talk on here a couple of weeks ago, and David Cornu told me about using dropout as a means to get at the probability distribution. So I guess you could have done that as well, right? With a regression and with dropout to give you that information.
Yeah, but dropout is more for the overfitting problem. But
yes, but you can actually use it to get
but then you have to generate. So the nice thing here is, in one shot you get the PDF.
Yeah,
because you
kind of do it the other way as well. Actually,
you get the class. Here you will have to make several dropout. You will have to drop some neurons randomly, and I guess you have to do it a bunch of time.
Yeah, like 100 times perhaps.
Yeah. But yes, I mean, all the exploration domain is large, and we have immediately when we thought that it was working as we better than what we were hoping at the end initially, indeed, we stay with that, and we didn't explore more. So we explore the dropout for the specific problem of the overfitting. But so again, at the end, we find that just stopping at the right moment was doing the job. And so we stay with this. We are not using anymore the dropout approach. But I agree, yes, we can use it as well for uncertainties. But then did he compare with? I don't know what he was using for what he used that. But but if it was for photosy, did he compare with the pit statistic just to get an idea about?
No, I don't know. We would have. I don't think that we did that.
But at least
in this context,
maybe it's not exactly a PDF, but at least we have a pit test that shows that it behaves well. So then okay. I accept the criticism, of course. I have no.
No, it's not a criticism. I just wanted to know why it was. I had another question, but maybe I should allow other people to.
Go on, Rodrigo, if you want.
Oh, so the other question, thank you, was essentially as you change in redshift, your galaxy obviously changes size, right? And so, did you ever try the test of actually using the redshift to actually scale your training sample so that you took out that effect?
No.
Because that might be interesting, right?
It's even the opposite, indeed. So you can have even galaxies that are way larger than the stamps that we are doing. So that we don't know exactly the scale of the galaxy because it's just larger than the stamps. And you still get extremely, because usually that's a high signal to noise, and you are still able to get extremely pertinent redshifts, extremely good redshifts. So even with partial information on the galaxy when it's bright, large. So we haven't played the exercise to follow any scale, to get scale invariant, so whatever the size, very large for very small for, no, just for one simple reason, we train the network with a fixed size images. That's why we try to change the size of the stamps, but for all the stamps. Okay, so we try different size, okay, but we didn't mix the size.
Yeah, because it would be interesting to know to what extent that information is coming from the size of the.
But normally in the feature map, we should be able to extract pertinent information about. There is illustration of what the feature maps are doing, but here we haven't been able to have nice illustration of the different level of feature maps. What were the main information that they were able to extract from the galaxies? We haven't seen any particular feature that tell you, yes, here you can clearly see the age of those objects, and so it's kind of like people do in Goodfellows. You can really see nice images from cars also. You can see here it detects the age. Here it starts to detect the wheels, and so we don't have such a nice behavior in all the galaxies. It's much more noisy. Huh? Don't forget that all those images compared to what we see with classical images used by people for the faces and so on, the signal to noise is much higher, always. So, and that's why we see that way, obviously in our case also, when the signal to noise get better, the improvement is drastic.
Well, thanks again. Lovely work.
So it's in progress. Yeah.
Hello. Thank you, Stephane. I have 3 points in your 3 parts of the presentation. Say, first part on the CNN, you explained it with detail. I mean, the rate of the number of image of convolution blocks, what to say, to the compression or pulling of the size. How do you optimize? I mean, you said that. I mean, you have a network. I mean, very large. I mean, and how you the output of that? How do you optimize? How many rates? how many compression, I mean, and how much of time do you need? I think that I would like to, I mean, that is one point. I have two others.
Indeed, but that's interesting because that's exactly the experimental part. We tried different blocks of convolution. Inside one block, you can even add more convolution. The point also, there is one important thing is when we say convolution is not something that we decide to do. So we decide the size of the kernel, but every value, so it's not a specific convolution by a Gaussian of this width.
Yes,
I
understand.
All the convolution, all the kernel value are also trained by the network. So it will optimize all the value inside this convolution kernel. And it's true that you can have improved performance, and indeed that's why we improve compared to the result I show. We have slightly better results now because indeed we have more convolution applied. Not more pooling, so we stay with three or four poolings, so reducing the size of the feature map. But we have applied more convolution per block, and so we have a wider, in that sense that we apply more operation at the same level of the block. And but this is experimental.
Yes, but it's experimental. But afterwards, you can infer some law, some I mean empirical improvement, optimization. I mean information theory or modern information theory could help. It's very interesting because you have I mean millions of.
No, I agree. But basically, they use everybody start with standard networks that has ResNet or networks that already exist, and then you slightly modify. And basically, the last improvement done on the code was essentially to make it slightly to apply more convolution per level. And why? Just because Jérôme tried and he found that at the end he was improving the results. And but yeah, we didn't try to have any
clever. I mean, it is clever, but I mean more systematic in some sense. With
yeah, that will be nice. That's the frustrating part. That was also my concern from the beginning. I mean, you clearly see that the neuron is the CNN can handle so well the galaxy inclination. So. And I would love to use this information to learn about the dust attenuation, because when I do IC defeating, I'm interested to know what the physics I should include to better model the galaxy.
Precisely, that's what I mean. That's what I
you don't learn anything. You do well, but you don't learn anything.
that is what precisely. So thank you. I mean, the second, I mean, we could discuss much more, but I mean, the second on this, I mean, the second point is, which I found very interesting, is this, the fact that you can have this unlabeled set to combine the set, different sets in what can be concatenation blocks. And that you should check too an internal consistency of what you are combining, and how much. I mean, have you applied to other set to set with different redshifts, for instance, to try to cover? I mean, to go deeper with these methods, I mean, trying to take profit of the data you could have access.
Yeah. So that's the idea, but we don't have results yet, so I cannot really give a detailed answer. but really I think what we are missing right now is the use of, because we have plenty of images, so we really need to go through this. So through the unsupervised. So unsupervised is one thing. So to try to match a different representation of similar of images seen in two different with two different telescopes, for example. And for that, we don't need the label. And this, you can already optimize the latent space for that. And but I cannot tell you the benefit of doing such approach because we don't have yet results. So I cannot tell you more about that. I hope it will be useful and efficient to go in that direction. It should be because it can learn. We have plenty of objects in common between the different, so to do the domain shift, and so we hope that this will help greatly the improvement. And basically, the nice thing is it covers the full redshift domain and magnitude range, so you can really go. I'm not talking about comparing SDSS with HSC. I'm really talking about comparing, for example, CFH-CLS and HSC, which is already too deep domain. You are already exploring a large redshift range in both sample. And so it's not like in one domain you see high redshift objects and in the other it's very local. Okay, so it's basically in the similar domain range of flux and redshift. So, but then you benefit because they are not all located in the same region. So you optimally exploit the common area to join the two surveys in one.
In any case, even for consistency of the different sets, I mean, it's very, very interesting to explore. I mean, it's
yeah. But the most difficult is really the last part from Reda, what is starting, because we do the assumption that there is no initial overlap between the two domains. So you need to go first in more abstract domain. And this is more complex. So by philosophy, it's much more complex. The first approach, I hope that will be I hope that the first approach from Jérôme will be efficient because it's really, let's explore and use even unlabeled data, but that are in common between two domains. And
thank you. Last, but I think not least, concern. I found very nice your introduction on the cosmic web, and it connects with your conclusion when you said for the cosmic wave reconstruction and evolution. I mean, that could help for galaxy formation. So that is a comment. Don't forget that going to deeper surveys, also the nature of dark energy come about. You need to have an information on that. I mean, also to disentangle the same nature of dark matter. Also, the number of mergers. I mean, the observation of mergers. Mergers are there and came out in the simulations. That's, I agree. But I mean, the number of mergers or the number of mergers or the merger rate is something which need observations. And that what we know from HST and hopefully from others. I mean, Vera Rubin now. I mean, if will come out soon. So it's very important also to know that is connected with the environment. I mean, the influence of environment. So it's not that part is not too clear. I mean, we need, because the different models of evolution and the nature of dark matter give different type, of merger rate and of course of evolution. And you know that observations do not give a high number of merger or what is called different type of merger too. So it's just a point to take in mind, and the surveys, the observation will be very important. Of course, the methods to disentangle that, also.
Yeah. Yeah. Here indeed the cosmic, one of the hope, and all this work indeed is, if we can extract the cosmic web is one thing, but the idea is also to try, because there is this theory from Sandrine Collis and Christophe, all the team of IAP, where you can follow the connectivity of the cosmic web, and that's probably what motivate me first for this work is if we can get a fair description of the cosmic web with photosy, then we can use LSST to check, because connectivity on maxima will behave with redshift in a cosmological way, so it will be sensitive to the cosmology. So if we can follow this connectivity with the redshift based on the photosy and then LSST, which will be statistically very gigantic, then we may have some hope to distinguish some cosmological model.
But connectivity is connected with lacunarity, is connected with sparsity. All this which came with voids too. It's all connected, and that depends also of the growing rate, the merger. The growing of a structure, the growing rate, which is very important.
But the connectivities may be something which is quite easily stable enough statistically to cover. And in terms of maxima, because you can pick up easily the peak of the density field. So even if your photosy are not very accurate, or you have some mismatch and so on, you can still pick up the maxima. And then you can, my feeling is it's the numbers, the connectivity is a number that you can probably get right easily when playing with photosy. So that's my hope. So and then it will be a useful statistic to check with the redshift.
Thank you very much, Stephane.
Thank you.
Thank you to you, and sorry for it being so long.
No, it's okay. I think we should stop now. I had several questions. I think I will ask you by email or later, but we should stop. Thank you again, everybody, for attending, and let's meet next week then.
Thank you.
Thank you.
Bye.
Bye.
Bye bye.
Si tu as 2 minutes, Stéphane.
Oui.
Le framework, c'est vous qui l'avez développé ou vous